So we're talking about chapter 5, energy, right? This is the topic for this week. And so again, the idea is after learning all these basics about mechanics, kinematics, and dynamics, we're going to advanced topics. So for the second half of the semester, we're going to learn those advanced topics, which are basically including chapter 5 and chapter 6, energy and momentum. And then these two are basically very useful concept to have in order to give you some like, to faster the way of solving problems. And then we have chapter 7 and 8, which is basically talking about the specific kind of motion, okay, which is rotation. And we start from talking about work in Monday's lecture. So the work basically is a way to describe the impact of a force to the motion you have, or the contribution. So you could either use impact or contribution, okay? And basically the definition here is, mathematical definition is this: it equals the force, the magnitude of the force times the magnitude of the displacement, which is the distance, times cosine of the angle, where the angle is the angle between the two directions, the direction of force and the direction of displacement. So that's how we define work, okay? And basically the idea is, depend on the angle. If the angle is 0, the force, you got a positive number, then it's like you got a positive contribution. It's a maximum positive contribution. If the angle is smaller than 90 degrees, only one component of the force is going to do the work, but it's still going to be positive contribution. When the angle is 90 degrees, the force is going to go along this direction, so there's no contribution because cosine theta is 0, so there's no work. Now, when the angle is larger than 90, smaller than 180, like this, you're going to have a negative contribution. The force doing negative contribution, meaning it's kind of trying to stop motion instead of creating the motion. Okay. Finally, you have when theta equal to 180, cosine theta equal to -1. So the contribution totally negative. Okay, it's a maximum negative contribution. So it's going to be just going backward. Okay. So, and then we say that work is a scalar, okay? Although there's a sign, it could be positive or negative, but there's no direction for work, okay? So it's just a scalar, and then unit for work is just the Newton times meter, okay? Because the force times distance. So that equals to joule, okay? So let me emphasize again, when you try to solve calculate work for these quantities, keep in mind they are scalars, okay? They're not vectors, okay? I mean, just use their magnitudes for force and distance. Nothing about direction. So these two are always going to be positive numbers because they're magnitude only, and you cannot have negative magnitude. Okay, the magnitudes are always positive. Okay, and the sign of the work is coming from this cosine theta, this part. Okay, so with that, let's go to a example. Let's do this example 5.1. Okay. Sliding through the Yukon. Okay, so basically you have a man do ice fishing, pull a sled loaded with salmon there. Okay, you are given the total mass of the sled and salmon, which is 50 kilogram. Okay, and then you also given the force given by the man, which is 120 basically. Okay. And then it asks you how much work does he do on the sled if the rope is horizontal to the ground, okay? Like if you pull everything like horizontally like this. And also how much does he do when the angle is 30 degrees and for the same distance. And does that give you, yes, 5 meters, it gives you the 5 meters, okay. And then also ask you about what the work done by friction. Okay, this is a very, let's modify this a little bit, okay? But we'll use this context. I mean, we can add a little bit to it, okay? So let's go back to our whiteboard, okay? Let's do it here. So we're gonna just simplify everything by drawing a box here for the sled and salmon, and then we have this force here, okay, the pulling force to it, okay. To make it more interesting, let's consider a little more than what is talking about there. So sorry. Okay, so see, there are totally 4 forces on the, I mean, on this object. Okay, on the whole thing. Okay, it could be. Okay, let's do, let's say. So I mean, on part C, it says there is a friction. Okay, when in the service situation, but before part C, there's no friction. So let's do part A and B, but we'll consider more than just that work. Okay, so for part A and B, let's do that first. Okay. A and B, okay, no friction, okay. So the example asks you to calculate work done by this F here, but let's do a little bit more than that. Let's do work done by F, and I mean calculate work done by every force, okay. Work done by every force. I mean, this just give you some like a more, I mean, complete kind of discussion. So roughly, I mean, basically, you can see the definition work here, right? You can talk about work of any force you have. So if you have, like, say, 3 forces, then you can talk about 3 works, okay? And you can talk about the total work or work done by individual force, okay? So in this case, when there's no friction, how many force do we have? Because there's a contact to the surface, right? So, and we know there's always gravity, and then there, because of the surface, there's always normal force. So gravity is going down and normal force going up, and then we have this F here. So we have 3 forces, okay? And then, so let's try to calculate the work done by each one of them, okay? Let's start from the normal force and gravity, okay? So let's start from gravity, okay? So let's use the definition here. I'll just label this as G, okay? So according to definition, equal to force times distance times cosine theta, okay? Well, in the case of gravity, you do not need to know the values here, because this is the direction of the displacement, right? I mean, sometimes if you want, you can draw this to remind you. You can draw like delta R or something to remind you this is the direction of displacement. When you calculate work, it is important to know the angle here, right? So what is the angle between this direction and that direction? Direction of the force and the direction of displacement. Send me a message. What is the angle between these 2 directions? Come on, guys, that's a simple question. If you want, can talk to me as well. Okay, I got one answer. Again, I'm just trying to do this kind of interaction, you know, interactively with you, so that can kind of help you to get engaged. Okay, I got one answer. Anybody else? Angle between this direction and this direction. Okay, I got 2 answers. Okay, so I guess it's better than 1. Okay. So basically, the angle is 90 degree. Great, 3 answers. Okay, so 90 degree, right? I mean, I guess it's too simple. So some of you guys feel like it's a waste of your time to answer this question. So now angle 90 degrees. So we know cosine 90 is just 0. So if you want, you can put 90 there. Okay. Now, I mean, maybe put mg here instead of F, because that's the force you have. That's the let me erase this. Okay. Okay. Put mg here. So the force mg, distance d is 5 meter, and then the angle is 90 degrees. But you don't have to go ahead and calculate, because this cosine 90 gives you 0. So this work is 0, and as it should be, because this force is going on perpendicular direction of the displacement. Okay. Similarly, you can calculate work done by normal force. It's the same formula, FD cosine theta. And again, you have ND, and then this angle theta is again 90 degree. So this is going to be 0 as well. Okay. So this is 90 degree. Okay. It doesn't matter for A or B. Both cases, these 2 forces are doing 0 works. They have no contribution to the motion. Okay. Now let's do part A then. It basically says when the force is pulled, let's see, horizontally to the ground, theta equals 0. Okay. Again, we would start from this definition here. We write WF equal to FD cosine theta, and we know theta is 0. So you have FD. F is okay. F is given, right? So F is given as 120 Newton, and D is given as 5 meter, and then M is 50 kilogram. Okay, let me maybe write them down here. So F is 120, D is 5 meter, and M is, see, I have short memory now. M is 50 kilogram. Okay, 50 kilogram. Okay, so these, okay, so kilogram, not gram. So these 3 pieces of information, okay? So put them in here together. You have 120 here times distance, which is 5 meter, times cosine. Well, in this case, it says theta equal to 0, okay? Cosine 0 degree. Well, cosine 0 is 1, so it's just equal to 120 times 5, which gives you 600, okay? Newton times meter is joule. So the work done by the force in part A is just 600 joule, okay? Now in the second case, you have a very similar situation, but B here, okay? Now the angle is not 0 degree, but 30 degree, right? Let me double check, 30 degree, yes. So, and the formula is the same. So you do this, okay? Work equal to force times distance times cosine 30 degree, okay? Now plug in everything here. For the force, you have 120, and then distance, you have 5 meter, and cosine 30 degree. You just calculate it, right? It's like 0.8 something. Okay, let me just do it. Cosine 30, okay. Yeah, 0.866, okay. So put them together, you have basically 600 times 0.866, right? So go 519.6. I'll just round it to 520. Okay. Joule. Okay. Now you see that the work are the same and the distance travel are the same, but the work done, sorry, the force are the same. The distance travel, the magnitude of the force are the same. Distance travel are the same, but the work done are different. Okay. In the first case, it does more work than the second case. Okay. And you may think about, I mean, the reason is because in the second case, only one component of the work, force, is doing the work, while the other component is not doing the work. You may think that how could it be possible, like the same, I mean, you put different angles. It seems like in both cases the object moves, right? But there's a difference here because in the first case the force is pulling at the 0 degree, so you have a bigger acceleration. Actually, it's going to be in the second case, you have smaller acceleration. So the speed of the object in these two cases are going to be different. Okay, although the distance travel are the same because the force is pulling at different angles, so going to have different speed. Okay. Now anyway, let's go to part C. So in part C, you're asking about so there's some friction here at the coordinate position 12.4. The main there's a friction, okay, of 45 Newton. And then all the way to 18.2. Okay, now it asks you how much work is done by friction. Okay, so 12.4, 18.2. And then the friction is 45 Newton. See, I mean, yeah, 45 Newton. Okay. 45 Newton friction. Okay. Now the question is how much work is done by friction, right? So first of all, you have to know the direction of friction. As we know, because it's moving, right? So it's definitely a kinetic friction. Sorry, kinetic friction. And then the friction is always going to the opposite direction of motion. So this is going to be, if the object goes this way, the friction going backward. Okay. So, and then you still use this general formula. Okay. Okay, so the force is given by friction, which is 45 Newton. The distance, well, it's for this specific distance, right? So it's gonna be 18.2 minus 12.4. Finally, cosine of the angle, right? What is the angle here? Send me a message. Oh, there's a message right here. Let me see. There's a question or. Oh, how are we going from Newton to Joule? Okay, I'll explain that. Maybe you already seen that, but tell me what is the angle here in this case when you have when you consider work done by friction? What is the angle between the direction of friction and direction of motion? Send me a message, guys. Okay. Yes, 180. That's correct. Yes, because one of them going one direction, the other one going to the totally opposite direction, right? So this is the direction of motion. This is the direction of a force. So this is the angle 180. So you need to plug in cosine 180 here, okay, for the work done by friction. And if you calculate cosine 180 is exactly -1. So you have it give you a minus sign. So minus 45 times this is basically 5.8. Okay, then the Newton times meter. Right, this is 5.8. So okay, so that's gonna be your work. Okay, now the rest is just calculation. 4.45 times 5.8. So you got 261. Okay, for this last part. Okay, so the work is negative because the friction is going opposite to the direction of motion. So it's doing a negative contribution to the motion. Okay, so that's why you got 261. See, basically this, and then these are what we calculated before. Okay, so what I want to say here is, I want to emphasize again. Okay, using this formula is simple. You know, just plug in numbers, but you need to know definitely this part here is critical. You need to know what angle you're talking about. Okay, and the angle always refer to the angle between the direction of force and the direction of motion. Okay, and for this first two part, just plug in the magnitude. Okay, for the force and magnitude for distance. Okay, and that's the correct way to do it. Okay, so any questions about this example? Do you guys feel it's a little bit simpler than the Newton's law problems? Yes. Okay. So see, this is the kind of a problem you solve for work. Now notice that I mean, in this case, it gives you the force value, right? Like a friction as well. But sometimes you may need to figure out the friction. For example, in this case, if we give you the coefficient of a kinetic friction, because you know the normal force, you would be able to calculate the friction as well. So anyway, but that's pretty much what kind of problem you expect for this. Okay, so now let's move on. After we talk about work, okay, let me go back to this question asked by students. So to go from Newton to Joule, it's like you when you're calculating work, right? You have force times distance. So that's why the unit that is Joule, not Newton anymore. So it's a totally different quantity. Okay, so you have to take you have to take here Newton, and then times meter to get joules, right? You have to have these two multiplied together. Okay, hopefully this answers the question. Okay, so let's go to the second topic here. So we're done with work. Now let's talk about kinetic energy. Okay, I have another message here. Hold on. Okay, good. So okay, let me. So there's some relation between work and energy, but let's start from introducing kinetic energy by itself. Okay, so the definition of kinetic energy. Let me make sure I have the same notation as the book. I want to make sure that the book use what does it use? Okay, hold on. KE. Okay, so we're gonna use that as well. So the definition is pretty simple. Okay, let me write it down first. Okay. So kinetic energy defined as 1/2 mv squared. Okay, m stand for mass and v stand for velocity or speed actually, because velocity, I mean, it's actually squared, so it's actually speed. Okay, so it's pretty simple definition, and the meaning is also pretty simple. Basically, what it's saying here is, as far as something's moving, it has a kinetic energy. Okay, the faster the object is moving, the bigger the kinetic energy it has, which makes sense, right? You would expect that to be the case, right? Intuitively, right? And also this mass here, I mean, the bigger the mass you have, the bigger the kinetic energy. Same thing, right? So I guess both of these is pretty reasonable to expect, right? Don't you agree? It's kind of intuitive. Now, so it's the first important energy we have in mechanics, and there's another energy we talk about later. But some of you may wonder, why do we need this 1/2 in this definition, or why do we need the 2 here, a square here? Can't we define kinetic like mv or something? Why do we have to consider it to be square? Okay, that comes in for the relation between work and kinetic energy. So let's consider a very simple case. Consider a surface, horizontal surface, and you have a block on the surface. And then consider there's a force going, putting it forward like this. Now let's say this force is the only force, okay, on the object, okay, along the horizontal direction. There's no friction, no friction. Let's try to calculate the work done by the force, okay, based on the formula here, right? We'll have the force times the distance, whatever distance it traveled by the object, okay? And then cosine theta. But in this case, because the force is going horizontal as well, so theta is 0, cosine theta is 1. So in this case, it becomes FD, okay? But we can actually write FD a little bit different way. So remember, okay, we can write our F to be mass times acceleration according to Newton's second law, right? We can write our distance to be VF squared minus VI squared divided by 2A, okay? Well, this part comes from one of the kinematic formulas we have. Remember, we have something like this, delta x equal to VF squared minus VI squared divided by 2A here, right? Well, in this case, well, strictly speaking, it is the absolute value of that is the distance. But in our context, the force pulling this way is going to speed up the object. So it's going to be positive anyway. So that's going to be the expression here. So we can simplify a little bit. We can divide, I mean, we can cancel A from here and here, and then we'll end up with this 1/2 m VF squared minus 1/2 m VI squared. Okay. Now, what does that tell us? Okay, notice this is nothing but our definition of a kinetic energy. So we could actually write this as KE final minus KE initial. Okay, so final kinetic energy minus initial kinetic energy. Okay, so as we see here, we define our kinetic energy using this 1/2 mv squared combination. It turns out that the work done on the object equals to the change of kinetic energy. So this is you can write this like delta K, delta KE. And by the way, this actually is the total work in this case, okay? Because there's no friction and the normal force and gravity does not do any work. So the only work is done by the pulling force. So that's the total work. So it turns out that this is not only true for this specific case, it is true for every cases, okay? So this is actually a general law. This is actually called work kinetic energy theorem. Energy theorem. Okay, work kinetic energy theorem. So this is what we're talking about. Okay, so I mean, defining kinetic energy in this way help us to have this relation between work and kinetic energy change. Okay, so how do we understand this simple equation? It's very easy. Basically, what we're saying here is when you put the total work on, I mean, you do work on the system, the kinetic energy of the system increases. When you do negative work to a system, the kinetic energy of the system decreases. So so that way, work is directly related to the energy of the system. So So that's a better way, a more quantitative way to talk about the contribution here, right? Here we're talking about the contribution or impact of the force to the motion. But essentially what we mean here is the energy, how the work changes the energy of the system. And we see here that the work is, total work is directly related to the kinetic energy of the system, okay? Does it make sense to you guys? Okay, let's talk about the unit of kinetic energy, right? Now, from one point of view, because kinetic energy change is just equal to work, so that suggests us the unit of kinetic energy must be joules as well, right? But based on the definition here, like this combination here, right, is basically kilogram times meter per second square, right? By the way, this is our first test, the first homework, multiple choice question in our test, right? So this gives us another unit. So it seems like we have two choices of unit. Which one, is there any contradiction, or which one is correct, right? This is our question, right? So actually there's no contradiction here because they're the same units, because remember joule equals to Newton times meter. Well, Newton, remember, it's like MA, right? So it's kilogram times meter per second square, okay? And then times meter again, okay? So that gives us nothing but kilogram times meter square per second square. So they have the exactly same unit. So that basically means that the energy has a unit of work, okay? They're essentially the same thing. Now, another thing we want to understand is whether it's a scalar or a vector. What do you guys think? Send me a message. Okay, I got a bunch of different answers, scalars, vectors. Okay, the answer actually it is a scalar, okay? Energy is, Ke is a scalar, okay? So there's no direction associated with it, okay? Not only about that, okay, if you look at the definition here, right? Okay, Ke equal to 1/2 mv squared. So it's actually, it cannot be negative as well, okay? The value of kinetic energy is either larger or equals to 0, okay? It can never be negative, okay? Because you have a square here, right? You wouldn't be able to get negative numbers of a square for a real number of velocity or speed, okay? Now, why is it a scalar? For example, if you have an object, right, it's moving to the left with velocity, with speed of, okay, let's say -3 meters per second, okay, with velocity -3. Another object is moving to the right with 3 meters per second, okay? So they have the same magnitude, but going to the opposite direction, okay? Now, when you do this calculation here, you're taking square, right? So it doesn't really matter, you know. The first kinetic energy will be like let's say mass equal to 1 kilogram. So for the first object, you have 1/2, then 1 kilogram times -3 meters per second square. And then for this one, you have 1/2 times 1 kilogram, okay. And then 3 meters per second squared. So in both cases, it's going to be 4.5 joule, okay. So the sign doesn't matter, okay. Now in more complicated case, you could have velocity going different directions, right? And in those cases, you can show that again. I mean, you can just basically take the magnitude of the velocity and then take square of it, and that's going to give you kinetic energy. So kinetic energy is a quantity that has no direction in it, okay? It doesn't care about direction, it only cares about the magnitude, okay? So it's a scalar. And you have this, okay, so now what do we do with kinetic energy? Okay, it's pretty straightforward to calculate kinetic energy using the basic definition, right? As far as you know the mass and you know the speed, you could go ahead and do this, plug them in to calculate kinetic energy. That's pretty straightforward. Now, the thing that we do need to, I mean, we want to kind of demonstrate is how to use this work kinetic energy theorem to do some calculation. And as I said, energy is an advanced concept in mechanics. It's introduced to kind of help us to solve our problems easier so that we don't have to go to Newton's law every time, okay? So let's give a new example, okay, of doing that, okay? So this example is not in the book, but I think it's a pretty good example. So let's consider our free fall motion. Okay. I didn't have enough sleep yesterday. So, okay, free fall motion. So let's consider an object is dropped from the rest and then falling down. And let's say the object is gonna be like starting, I mean, a given height. Okay, let's say, say the initial height is h naught. Okay, and then let's say suppose we're interested in the speed of the object when it reaches a certain amount of height h. Okay, well, this h could be anything, right? How do we solve this kind of problem? Okay, now we can solve this problem by using our kinematic formulas. And if you remember, one of the formulas says delta x equals to vf squared minus vi squared divided by 2a. Okay, in our case, vi is 0, and so a is just basic g, right? It's g 9.8, right? Go let's say define this as positive direction. So you could actually write down. So what is the displacement? The displacement would be going down is positive, right? It would just equal to h naught minus h. So if you plug this in there and then use g here, 2g vf squared minus 0, right? You give if you get vf equals to 2g h naught minus h and square root. Okay, and so we can solve this problem using our kinematic formulas of constant acceleration. However, there's a very good chance that you won't be able to remember this formula, okay, out of your on top of your head. You probably need to look it up, you know, or maybe you use the wrong formula or something. Okay. Now we can now do this problem a little bit differently. Okay, we can use work kinetic energy theorem to do it. Okay. Now based on our definition, I mean our theorem, you have this. Okay, W equals to. So this is a total work. Okay. So sometimes we write like this: sum of work, that's total work, equal to change in kinetic energy. Okay. So how do we do this? How do we use this one? Okay. In order to use this one, we have to clear about what is the work involved in this case. Okay. Now when it's in the air, there's only one force doing the work, which is gravity, right? So that's it. So so we're talking about work done by gravity in this case. Okay. Equal delta Ke. Okay. Now we need to calculate this work. Okay? So gravity, the force is mg, right? We know that. Using the definition here, right? It's force times distance times cosine theta, right? So this is going to be mg for the force. The distance here is just this height difference, right? So that's the distance. So it's going to be h naught minus h. And then cosine theta, right? What is the angle theta? It's going to be 0, right? Because see, the gravity is going downward. Okay, see, as the object goes down, right? Okay, sorry, here. The gravity is going downward, and then the displacement is also going downward. So they're going along the same direction. So it's going to be cosine 0, okay? And that equals to delta Ke, where we can write it down. So, I mean, equal to 1/2 m vf squared, okay? Minus 0, because initial kinetic energy is simply 0. 1/2 mvi squared, vi is 0. So that's going to be our formula, okay, for this specific problem, okay? Now again, cosine 0 is 0. I mean, so it's 1. Cosine 0 is 1. So you have, and you see the, okay, so you got this, okay? Mg h naught minus h equals to 1/2 mvf squared, okay? So, and then you can divide m on both sides. So m is canceled out. So, and then you multiply 2 on both sides and then take square root. So you got vf equals to 2g h naught minus h and then square root. And then that's it. Okay, so you got the answer. Does this make sense to you guys? Any questions? Good. Okay. Well, do you guys like this way of solving problem? Or which way do you prefer, the first way or second way? Send me a message. Okay, first, yeah. Okay, see, you're totally biased, okay? The reason you're biased is because you learned first way already. Well, the second way is totally new. So therefore, you have a bias because this is something you're already pretty familiar with, so you definitely want that way. Well, I guess in this case, it's not totally convincing that you should use the second method. In terms of difficulty level, it's probably comparable, you know? I mean, this or that. Well, this require you to remember this formula. Well, in this case, I mean, you still need some formulas, but there's nothing to remember because this total work kinetic energy is just something really easy to kind of understand. And then the definition work is also pretty simple. Definitely kinetic energy is simple. Well, not now because this is new for you, but after a while you see it's simple to kind of even memorize them, you know. But anyway, I don't blame you, you know. And later on, we'll develop another way to solve the same problem. And then at that point, you should definitely fall in love with the new way, you know, maybe not right now, but anyway, I'm giving you this one example here. Use this work kinetic energy theorem to solve problems, okay? Okay, I got a message here again. Oh, first, okay, I have 3 for unanimous so far. Okay. Yeah, you guys probably want me to stop lecture for the whole semester right now, and then, okay, so, so we're done with the discussion of this of the second topic, which is kinetic energy. Let's go to the third topic. Today we need to finish early, but we still have like 15 minutes. Okay, so okay, we haven't done exercise for a while. We'll probably do one tomorrow. Okay, so the next one we do is we call potential energy. Okay. And specifically, we're going to talk about something called gravitational potential energy. Okay. So what is that? Okay, it's basically saying that okay, I think it's called PE in the textbook. It's defined as this. Okay, M, G, and H. So this M here is the mass of the object. G is just our 9.8, and H is the height. So MGH. That's the definition of potential energy. Okay. Okay, now this energy is a little bit harder to understand. Okay, so for example, why does an object has an energy? Simply because it's staying some given height. Okay, so kind of weird, right? And then as you see from that definition here, the higher the object is, the bigger the potential energy will be, right? So why is that? Okay, what does that mean? And again, fundamentally we would start from talking about work. Okay, I mean from work it's kind of naturally go back to this concept. But before that, we can do a simple demonstration here. Normally when I do it in class, I would do it using like a piece of chalk. Well, I don't have a piece of chalk in front of me, and but let me just kind of explain like this. So you say you have an object, right? It's at some height from the top of the table, right? Now, according to this definition here, the object has some potential energy, right, with respect to the table. So what does that mean? Now, if I bring it higher, it has higher potential energy. What does that mean? Well, think about this way, right? You hold this object in your hand, but if you're not careful enough, the object may fall off your hand and then go down like this, right? Well, you can imagine the higher the object is, the bigger the impact will be when it collides with the table. Does that make sense? Or maybe you think about an extreme case, right? Like a person, right? Let's say think about a person jump out of a, I don't want to put any negative example, but I want to give you kind of impression. Okay. I mean, maybe not a person, a dog. Like a dog jump out of a building. Okay. Think about if the dog jump out of the second floor, right? Maybe the dog is going to be fine, maybe broken leg or something, but it's fine. But think about it, the dog jump out of 100 floor of a building, probably the dog's going to die, right? Would you agree? Because it's going to crash so hard to the ground, you know, when it jump from so high. Now, why? What is the difference here? Well, the difference in this concept of potential energy, you know, the reason that you have a higher, impact when you crash, you know, is because you start from a higher position, so you have a higher potential energy to start from. Okay, so this definition of potential energy has some real consequence in your life, you know, or in everybody's life. The higher the object is, or the higher you are, the bigger potential energy you have, and you should be really careful about it, because this energy, although it's not working right now, if you're not careful, you could fall off, and then it could cause a lot of damage. That's why it's called potential energy. It's not doing anything yet, but there's a potential, okay, that it can do something. And then the higher you are, the bigger the potential. Does that make sense, you guys? So next time when you go to a national park, like you climb to a very high mountain or to a cliff or something, you stand by the cliff, you feel like your whole body is shaking, you know, you're so scared of this cliff or the height. Don't blame yourself, you know. It's just your subconscious has realized the potential danger there, because you have a very high potential energy there, okay, because of MGH, the height, okay. So it's just a natural, it's your intuition to feel this big potential energy, you know. That makes sense to you guys? Okay, so let's try to consider this from the work point of view, okay. We have 8 minutes, so we'll see what we can do. So let's go ahead and calculate something, okay. So consider two cases. In the first case, the objects fall directly, okay, from certain height to the ground. It's doing a free fall, okay. In the second case, the object is not doing a free fall, but going along a ramp, like this. And this is the same height, okay? The height are same, okay? So this is case 1, this is case 2. Now my question for you guys is, in which case does gravity do more work? Okay, gravity is like weight, right? mg. In which case, okay, this is not work, okay? We use the same symbol for weight and work. Unfortunately, because we only have 26 letters in alphabet, so we sometimes use same symbols for different quantities. So the weight equal to mg, right? So which case does this one do more work? Does the weight do more work? Just send me a message. Tell me based on your intuition. It certainly doesn't need to be right, you know. It may be wrong, but it's good to know this, you know. I mean, it's good to try. Okay. Okay, I got second case should be the same. Okay. Okay, good. I got a couple of answers. The free fall. Okay. Yes, actually, it's interesting, right? Because you feel like, some people feel like it might be the second case because it seems like the displacement, the distance is longer. Well, some people feel like it's the first case because it's the gravity is going like directly along the direction of motion, and some people think it's the same. Actually, the answers they're the same. Okay, it's an interesting answer and it's a very useful answer for us. So let me calculate. We have 6 minutes here, so let me just go ahead and calculate this, and then we'll call it a day, and then tomorrow we'll continue. Okay, so let's consider the work done by the first case. Okay, again, I'm just using still the definition of work. Okay. In this case, the force is just the weight, mg. The distance is just h. That's how high it goes. And then angle theta is 0, so cosine 0, okay? So that gives you nothing but mgh, okay? Well, in the second case, it's a little more complicated because the distance going along is not h, right? Let's call this angle theta here, okay? So this distance here is going to be, maybe let's call this angle alpha. Okay. So this distance is using trigonometry here. The distance in the second case is going to be h divided by sine alpha, right? Because sine alpha equal to d h over d. So that's the distance. But the angle theta is not 0 anymore as well, because the force is going this direction, the displacement is going this direction. So the angle theta is this angle here. So and this angle has, it basically is this angle. So this angle is not alpha, but 90 minus alpha. So the work done by the gravity in the second case, if you use the same definition here, you have mg times d, which is h over sine alpha, times cosine theta, which is a cosine 90 minus alpha. Okay, so this looks very different from that, but if you know some trigonometry, you know that cosine 90 minus alpha equals to sine alpha, okay, in any case. So these two actually cancel out. So in the end, you got mgh, which is the same as the first case, okay? So in both two cases, the work done by the gravity are the same, okay? And actually, not only for this case, you can show easily by some argument that even for like very irregular paths here, as far as the height change the same, the work done by gravity are going to be the same of all the cases. Okay, in this case, what you can do, you can break this whole thing down by a bunch of small ramps, at different angles. See, our discussion is independent of the angle, right? Because we always got the same thing. Doesn't matter what angle is. So if you can break this very complicated curve to many small pieces of angles, piece of ramps, you conclude that this work done the same as this time, this case or this case. Okay, so in all cases, the work done are the same. So this is a very special property. So for the force that do that is called they're called conservative force. Okay. So definition of conservative force, the work done by the force is independent of the path and only depend on the initial and final height. Okay, or yeah, only depending on initial and final state. Okay, so this is our message here for, okay, and then we'll show that because this gravity is conservative, we can define this potential energy. So in physics, conservative is totally good, While in politics, it depends on which party you vote for. But it has a totally different meaning, like in physics. So in physics, we want conservative forces. Okay, it's easier to deal with. Okay, so I guess let's stop right here.